Hello, good morning. I am Ramjee Singh Prajapati, Assistant Professor, Fire Technology and Safety Engineering Department, IPS Academy. Today we have discussed the dynamics of fluid mechanics. Firstly, we have discussed the what is the fluid. Basically, fluid is the substance. Fluid is the substance. It is substance that capable to flow. Any substance which is capable to flow, that is the fluid. Fluid is a substance that deform continuously when an external shear force is applied on it. That means fluid is the substance we have applied the force, and that is the shear stress. Due to the shear force, it is easily deformed. That means no external resistance in the between the molecules of the fluid. The continuous deformation of the fluid does not stop until the force is removed. And in simple way, we can say that the fluid is a substance which offer no resistance. That is means flow, it has means no resistance. If applied any substance, it applied the shear force and has no resistance. So further, it can be easily deformed. It is easily deformed. So we can say the fluid is a substance which is easily deformed applied after the shear force. Deform continuously as long as any shear stress is applied. Substance with no strength, that is means if resistance is weak, that is means no strength. And deform when force are applied. In the fluid include the water and gases. Generally, we have taken the fluid, water and gases. That is the fluid. And fluid, the various application of the fluid in nowadays day-to-day life, we have discussed the behavior of the fluid and flying of the birds, flying of the aeroplane, and fly of the wind. That is the all the application of the fluid. So that is the next, the types of fluid. Types of fluid, mainly there are two types of fluid. One is the ideal fluid and another is the real fluid. So we have discussed the types of fluid. Types of fluid. Fluid one is the ideal fluid. Ideal fluid, that is means ideal fluid, that is means no viscous. That is means no viscous. No viscous. The ideal fluid, a fluid is non-viscous, incompressible. Incompressible, that is means density is the constant. It is an imaginary fluid which does not exist in reality. In actually condition, in practical condition, ideal fluid does not exist. And second one is the real fluid. A fluid which have the properties such as the viscosity, surface tension, etc. Generally, all the types of the fluid are considered as the real fluid. Here, as the fluid, real fluid, that is the fluid in which presence of all fluid property. Suppose it may be compressible, it is the viscous, it is the surface tension present in the fluid. So all type of, suppose that milk, suppose the any oil, petrol, gas, all the real fluid. And another is the Newtonian fluid and non-Newtonian fluid. So one is the Newtonian fluid. Newtonian fluid, that is means the fluid which obey the Newton's law of viscosity. The Newton's law, that is the Newton's law of viscosity, that is the shear stress is directly proportional to velocity gradient. So here tau is that is the shear stress, and du upon dy that is means change of velocity with respect to particular time. Here it is the proportional constant we removed, that is the mu du upon dy. Here mu that is the dynamic viscosity, that is means viscosity. So Newton in fluid, that is means all types of the fluid which obey the Newton's law of viscosity. For example, gasoline, air, light, oils, all the water also are the example of Newtonian fluid. And non-Newtonian fluid, that is means the fluid which do not obey the Newton's law of viscosity. If follow the Newton's law of viscosity, that is the Newtonian fluid, and it is not follow the Newton's law of viscosity, that is the non-Newtonian fluid. Suppose we have draw the graph between the shear stress tau on y-axis, and we have taken the du upon dy, that is means velocity gradient in x-axis. So we have plot it in the case of the Newtonian fluid, the shear stress is directly proportional to velocity gradient, that is means we have obtained a straight line, that is the Newtonian fluid. Newtonian fluid. If it is not proportional to, it is obey the Newton's law of viscosity, that is Newtonian fluid, and these are the non-Newtonian fluid. These are the non-Newtonian fluid. It's okay. And another is the example of non-Newtonian fluids are the plastic, paste, etc. Another is the dilatant fluid and pseudoplastic fluid. Dilatant fluid, apparent viscosity is increasing. That is means in case of dilatant fluid, tau is equal to mu of du upon dy. Here mu is that apparent viscosity. Apparent viscosity. In case of apparent viscosity, the afferent viscosity increase, that is the dilatant fluid, and it is decrease, that is means pseudoplastic fluid. In case of dilatant fluid, apparent viscosity increase with the rate of deformation, and hence these fluids are known as the shear thickening, because it is the increase the thickness. So it is also called the dilatant fluid, that is the shear thickening fluid. And example of the rice, starch, butter, sand, sugar, etc. And next is the pseudoplastic fluid. A pseudoplastic fluid, apparent viscosity decreasing. In case of dilatant fluid, it is increase, and in case of pseudoplastic fluid, the apparent viscosity is the decreases with the rate of deformation. With the rate of deformation, this is the decrease, that is the pseudoplastic fluid. Okay, these fluids are known as the shear thinning fluids. Example: blood, milk, paints, paper, pulp, etc. And next one, the ideal plastic fluid. So when the shear stress is proportional to the velocity gradient, that is means shear stress is proportional to the velocity gradient, and shear stress is more than the yield value, it is known as the ideal plastic fluid. Here this is the show the diagram and the ideal plastic fluid above in the case of the ideal plastic fluid. So next one, the Bingham plastic fluid. The Bingham plastic fluid is also called as the ideal plastic fluid. Example: suppose that in case of the Bingham plastic fluid, toothpaste, drilling, muds, etc. Certain fluids show variation of viscosity with respect to time. Suppose there are two types, thixotrophic fluid and rheopactic fluid. So in case of thixotrophic fluid show a decrease in rate of shear stress with the time under a constant applied shear stress. Example: lipstick and paints. For example, it is kept sometimes. So this is the thinning condition. So thixotrophic fluid and rheopactic fluid. The fluid phase require a gradually increasing shear stress. Increasing here, suppose this is the tau and velocity gradient. So this is the ideal plastic fluid. And in case of thixotrophic fluid condition, this is the thixotrophic and this is a rheopactic fluid. Okay. Next, the mechanics of fluid. Suppose mechanics of the fluid. Finally, we have discussed the mechanics of fluid. How to fluid how to fluid flow, how to analyze the behavior of the fluid, the study of motion and the forces which causes the motion. The fluid in motion due to the forces we have considered, that is the mechanics of the fluid. So fluid machinery may be classified in three categories. One is the fluid in motion and fluid in rest condition. So this is the fluid in rest condition. Fluid at rest condition. Rest, that is means fluid does not flow. As per the definition of the fluid is any substance which capable to flow. But here we have tell the fluid at rest condition. So it is means fluid, but it is prevented by external forces. So that is the statics fluid mechanics. Statics fluid mechanics. So in case of statics fluid mechanics, the study of the forces acting on the particle or body at rest condition. Suppose fluid in a container, fluid in static condition, the mechanics of the system of the fluid, that is the statics fluid mechanics. We have find the suppose that weight, that is the property of the fluid, that and pressure, find the pressure, buoyancy condition, that is the all in the statics fluid mechanics. And another the fluid in motion. Again, it is again categorized in the same two condition. Fluid motion, it category if force is neglected, force not considered, that is means force in motion but pressure force not considered. The fluid due to the flow we have not considered, that is the kinematics fluid mechanics. So that is the kinematics fluid mechanics. In case of kinematic fluid mechanics, why fluid is flow? So we have not considered the causes of the forces, causes of the motion of the fluid. So we have consider only the acceleration, velocity of a particular point of the fluid, that is the kinematics of fluid. So the description of the motion, displacement, velocity and acceleration, that is in category of the kinematics fluid mechanics. And another dynamic fluid mechanics, we have considered the forces consider, that is means fluid in motion and causes of the forces are considered, that is the dynamic fluid mechanics. The study of forces acting on the particle and bodies in motion, consider of these acting forces on the fluid particles. Next is the types of flow. So here this is the important point, how to classify the fluid flow. Mainly fluid flow in categorized in the various condition. So types of fluid, firstly we have classified the steady and unsteady flow. Steady and unsteady flow. So the steady flow and unsteady flow, that is means the fluid property does not vary with respect to time. So that is the steady flow. Suppose that dV upon del T equal to 0, del P upon del T and del rho upon del T. That is the steady flow. That is mean it is not dependent on the time. Suppose the fluid flow in 1 second, in 1 minute, that the flow is the constant, that is steady flow. Suppose we have considered the flow in this channel. So if the fluid in and fluid is out is the same rate, so it is the constant maintained. So that is the steady flow. And if the fluid property at particular point vary with respect to time, that is mean depend on the time, that is the steady flow. That unsteady flow, that del V upon del T does not equal to, that is the unsteady condition. Also del P upon of del T does not equal to, and del rho upon of del T does not equal to, that is the unsteady flow. And another is the uniform and non-uniform flow. So flow is the uniform condition, that is the another is the uniform and non-uniform condition. The uniform flow, that is means at any with respect to space, fluid property with respect to space, del V upon del S equal to 0, del P upon of del S equal to 0 and del rho upon of del S equal to 0. That is means fluid property does not vary with respect to space, that is the uniform. If the flow in the uniform condition, the velocity of fluid in a constant condition, and non-uniform condition, the flowing of the velocity is the vary with respect to space, that is the uniform and non-uniform flow. Another is the viscous and non-viscous flow. Viscous flow, that means have the some fluid property, that is the viscosity, and in case of non-viscous fluid, that is the inviscous condition. And another the laminar and turbulent flow. So this is the important laminar and turbulent flow, laminar flow and turbulent flow. So in case of laminar flow and turbulent flow, the flow of the fluid in suppose in good manner. So this is the laminar flow, and fluid in the flow in the zigzag way, and another condition, that is the turbulent flow. So suppose flow in the pipe, that is the example of the laminar flow, and the flow of the river and high velocity flow, that is the turbulent condition. So the laminar flow and turbulent flow, we easily find the help of the Reynolds number. Reynolds number, that is the inertia force to the viscous force. Finally, we have taken the Reynolds number, that is the density into velocity into diameter upon dynamic viscosity. So the density, diameter and viscosity are the constant in any cases. So the Reynolds number is directly depend on the velocity. If the velocity increase, the Reynolds number also increase. The higher velocity, that is tends to turbulent flow, and low velocity, that is the laminar flow. And another compressible and incompressible flow. So compressibility, that is means the compressed, the fluid in case of the compressed easily, that is the compressible flow. That is means it is change the density. Density does not change, that is the compressible flow. And incompressible flow, that is means density is the constant condition. And next one is the rotational and rotational flow. So rotational flow, that is means fluid rotate on axis. Suppose fluid is rotate condition. For example, in rotational condition, suppose this is the fluid particle, it is rotate. So suppose this is the, it is rotate on axis, on central axis, that is means suppose this is rotate. So this fluid is the rotate in circular fluid flow in the circular manner, and but it is also rotate on the on axis, that is the rotational flow. If the fluid flow in rotate condition, but it is not rotate on axis, that is the irrotational flow. and next one is the one dimensional, two dimensional and three dimensional flow. So in case of the one dimensional flow, fluid property it vary on x direction. Suppose fluid property vary only x condition, other fluid property v equal to 0 and another velocity component y and velocity component z direction also is 0. That is the one dimensional flow. And two dimensional flow, that is the fluid velocity of the fluid depend on the two direction. Suppose the u, x and y, and at another the v also is equal to a function of x and y and w equal to 0. That means third velocity component is the constant. So and three dimensional condition, the fluid flow in 3D condition, that is means depend on the x, y and z direction. So next is the continuity equation in fluid mechanics. So this is the continuity equation is the main important role play in the fluid dynamics and fluid kinematics. So continuity equation, that is means suppose we have taken the, this is the any two section, this is the 1 section and this is the 2 section. So at this condition, at this section, area of this diameter, this suppose the area of E1 and velocity of at this condition, that is the V1, and second section area that is the A2 and velocity that is the V2. And here if the fluid is taken, the density of fluid at one condition, that is the rho 1, and density of the fluid at two section, that is the rho 2. So here the continuity equation, this principle of the conservation of the mass, say matter cannot be created or destroyed during the flow condition between this 1 and 2 section. Mass of the fluid does not create or does not destroy. So this is applied in the fluid to fixed volume, known as that control volume. Mass, that is means mass entering per unit time, that is the mass equal to mass entering per unit time equal to mass leaving per unit time. So basically mass per unit time, that means rho mass per unit time at entering condition and mass per unit time at the leaving condition. So mass, that is the density equal to mass per unit volume. So in this equation we have find the mass equal to density into volume. So this is the density into volume per unit time and this is the density into volume per unit time. So in volume we can write the volume equal to area into length. So easily it is the rho and area into length upon time equal to rho into area into length upon time. This is the at one section and this is at the second section, that means another section. So length upon time we can write the velocity of the fluid. So this is the rho 1 A1 V1 and this is the rho 2 A2 V2. So this is the finally continuity equation in case of both compressible as well as in the incompressible. So this is the continuity equation. If it is continuity equation only in case of the incompressible condition, that is the density constant 0, that means A1 V1 equal to A2 V2, and in case of the compressible condition, the continuity equation, that is the rho 1 A1 V1 equal to rho 2 A2 V2. And we have discussed the finally dynamic of fluid mechanics. It is the basically the we have discussed the basics of fluid. So we have comes on the finally dynamics of fluid mechanics. Dynamics of fluid mechanics, that means we have considered the causes of the forces. The forces, that is means the Newton's law forces in the fluid, that is due to the Newton's second law of motion. So Newton's second law of motion. So finally, the dynamic behavior of the fluid flow is analyzed by the Newton's second law of motion, which relate the acceleration with the forces. The fluid is assumed to be incompressible and non-viscous. Forces acting on the fluid in motion, according to Newton's second law of motion, that is the force equal to mass into acceleration. Suppose we have considered in x direction, that is the net force acting in the x direction, that is equal to mass of the force and acceleration in x direct condition. So here various types of the forces are acted. One is the gravitational force, gravitational force due to the gravity, and one of the pressure force due to the pressure of the fluid, and the viscous force, that is the viscosity, turbulence force, surface tension force, compressibility force. All these forces are acted. So here we can forces is categorized in the gravitational force, pressure force, viscous force, turbulent force, surface tension force due to the surface tension, force due to the compressibility. It is equal to the mass and acceleration. Mass and acceleration. In most of the problem of the fluid in motion, the surface tension force and the compressibility forces are not significant. Hence, these forces may be neglected. If we neglect the surface tension force and forces due to the compressibility, so this is the reduced equation: forces due to the gravity, forces due to the pressure force, and forces due to the viscous force, and forces due to the turbulent force, that is the mass into acceleration. So this equation we can write the Reynolds equation of motion. So Reynolds equation of motion, that is means presence of the gravitation force, pressure force, viscous force, turbulent force. And for the laminar or viscous forces, the turbulent forces also become the less significant, and hence these may be neglected. That is, this equation further reduce. This is the gravitational force plus pressure force and force due to the viscous force is equal to mass into of acceleration. So this is the, again this is the above equation, that is the Reynolds equation of motion, and this is the Navier-Stokes equation of motion. This is the Navier-Stokes equation of motion. And further, again this equation is reduced. Only we have considered, so this the viscous force are also neglected. So this equation again write, that is the force due to the gravity and force due to the pressure force, that is the equal to mass into acceleration. So that is the Euler equation of motion. Euler's equation of motion, that is the Euler's equation of motion. Energy possessed by the fluid particle. So here the energy may be defined as the capacity to do work. The different kinds of energy possessed by a fluid particle are here. One is the potential energy, and second is the kinetic energy, and another the pressure energy. So potential energy of a fluid liquid in motion, it is the energy possessed by the liquid particle by virtue of the position. And suppose that due to the position, suppose the liquid fall in this flow, and that is the potential energy, that is the m into g into h. And another is the kinetic energy. So the kinetic energy, that is the due to this kinetic energy, any particle move. So movement of any fluid particle due to the kinetic energy. So we can write the kinetic energy is equal to half of mass into velocity square, that is the kinetic energy. And again last one is the pressure energy. Pressure energy of the liquid in motion, it is the energy possessed by a liquid particle by virtue of its pressure. The total energy of the liquid particle in motion is the sum of its pressure energy, that is means sum of this pressure energy plus potential energy, that is the pressure energy and potential energy plus kinetic energy equal to constant in case of the fluid in motion condition. That is the Euler equation of motion. So we have discussed the Euler's equation of motion. In Euler equation of motion, we have considered only two types of the fluid. That is the Euler equation. So we have considered that is the cylindrical fluid element, that is the cylindrical fluid element. So this we have taken, this is the ds, that length and area of dA, and velocity particular point, also the velocity, and pressure force. Here we two types of force acted. One is the pressure force and another is the force due to the pressure force and force due to the gravity force is equal to mass into acceleration. So pressure force along the S direction, that is the P, pressure force, pressure into area, the P into dA, and in opposite direction this force P plus del P upon of del S to ds into of dA. In this the opposite direction of in the downward direction. So and another the force due to the gravity force, that is the W equal to mass into gravity and particular angle. So this force is resolved in two direction. One is the component, this mg is in the cos direction and another the side. So its component, that is the sin theta, and this is the W cos theta. So easily this is the ds and this is the dz and this is the theta. Suppose that here easily W equal to mass into g, and this weight is resolved in two direction by the sin theta and another is the cos theta. Mass, that is the mass equal to rho into volume. So mass here W, that is the weight of the fluid, equal to rho into volume into g. So this is we easily rho into g into volume, that is the area into of displacement. Here the force acting on the cylindrical element are the pressure force P into dA in the direction of flow, pressure force P plus del P upon del S into ds into dA in the opposite direction, and weight rho g into dA into ds, and it is balanced, that is means net force is equal to mass into acceleration. So put the value of the pressure force and gravity force then in this equation. So that is pressure force P into dA, P plus del P upon del S into ds into dA plus force due to the W mg, rho into mg, that is the in case of cos theta in this direction. So this is the rho into g into of volume dA ds cos theta equal to mass into acceleration. So mass, that is the rho into dA into ds, and acceleration, that is the dv upon ds. that is the dB upon dt, and it is the multiplied by ds upon ds. So easily acceleration equal v into of dB upon of ds. It's okay. So put the value of acceleration and analyze, resolve this equation. So further we derived this equation. Finally it is derived this equation, and finally that is the dP upon of rho plus V into dV plus G into dz. That is the Euler equation of motion. It is represent P into dA, expand this, multiply this equation, and this is minus, and this is put the value of all the cos and sine, and finally divided by the density. So Euler equation finally derived after this Euler equation, that is the dP upon rho plus V into dV plus G into dz. That is the Euler equation of motion. First lecture we concluded, and in next portion of the fluid dynamics we cover in next session. Thank you.